There. In this video, we are going to talk about enterprise integration architecture. Modern enterprises are complex, distributed, multi-cloud enabled, and data rich. They may have a headquarters and multiple regional offices, and in each of these offices, they may have an on-premise data center, and collectively, they may have a cloud infrastructure in which they may be having applications and different data sources like databases and so forth. Enterprises' valuable data reside in systems of records, as we call it, right? And these systems of records uh, can include databases, CRMs, ERPs, HR systems, SaaS applications, and you name it. And these systems are siloed systems, and these systems need to collectively work to create value. And how do they create value? Is with digital experiences. And these digital experience comes mostly with applications. And this is how enterprises, users, employees, consumers, partners make use of the enterprise's data. And applications, or channel applications as we call it, is one way of doing it. And let's look at how application architecture has evolved, and let's look at some of those application architectures and see where integration fits in. So one of the earlier ways of creating applications was this thing called monolithic applications. Decades ago, enterprises used to build monolithic applications, and in such applications, usually there was a user interface, right? And these user interfaces use business logic in some form, and also it may have something called a data access logic, which may be connecting to systems of records, and that's where the integration happens. And even though I have shown this as a layered architecture in a monolithic application, all of these components, the user interface, business logic, and data access logic, are all bundled together as one deployable artifact, such as an executable file or a library or some sort of a deployable web archive kind of file. So, but internal implementation may really have some segregation in terms of how they have organize the code. But nevertheless, monolithic application means all of these are bundled together when it comes to the runtime. It's just one file that gets deployed into an environment, and that's what you will be running. But obviously, it's not a good architecture because you don't have separation of concerns, and you have possibly you will have scalability issues and so forth. And that's where other types of application architecture came in. But one important point here is to just understand, even in monolithic applications, integrations used to be there. And most probably that was in the data access logic. Another application architecture type was the two-tier client-server architecture. And it's very simple. There is definitely a server, because the client-server architecture, there's a server and there's a client, and client sends a request and gets a response from the server. And there may be like multiple clients sending requests or responses to the server. And that's a good thing, because server is there and there can be multiple clients connecting to it. And server itself might be doing like different logic, and one of that could be like various integrations, and those integrations could be with various systems of records. How exactly the server does this thing could vary, but mostly, and if you look at traditional types of servers like DNS servers or LDAP servers, and they may have mechanisms to connect with a database or a file system. Mostly, it will be created as a monolithic application, but there is no restriction as to how that server should be architected, and you can think of some of the other architectures that we're going to talk about in a while to create servers as well. And in fact, some of the architectures that we're going to talk about is an extended version of client server and architecture, because there is a client and there is a server, and how server is architected is what we will be looking at in the later sections on different architectural styles when it comes to integration. And another application architecture style that became popular when it comes to web in particular is this three-tier model view control architecture, and in that there is a client, and client is usually a browser. In this case, where a web application sort of is this presented to the user, and that browser will request something, a resource, to the controller, and that request comes to the controller, and the controller's responsibility is to instruct the model when to use the data, and instructs the model and what to use and so forth. And basically, controller orchestrates the model, and the model does the integrations. Basically, it connects with various systems of records, and it handles business logic and integrate with downstream applications and so forth. Once it gets the necessary resource related information from wherever it connects to, and that data is passed to the view layer, or the view part of this MVC architecture, and that view finally takes the responsibility to take the data from the model and format as needed for the client, and mostly the HTML format when it comes to web. So this is how the MVC architecture worked, and the important point here is to understand where the integration mainly happens, and that happens in the model level. And if you look at n-tier layered architecture, is an extended version of the three-tier architecture. Basically, you can consider three-tier architecture as a specialization of n-tier layered architecture. So here you will have multiple layers, and possibly there is a presentation layer, which could be in different technology terms. It could be an HTML file, a PHP file, JSP, ASPX kind of files, and there can be a business logic layer, and then a data access layer, and that's where mostly the integrations may be happening when it comes to connecting with systems of records. But the important point here is n-tier layered architecture. Now, in this case, it's a three-tier one, but it can have more tiers as necessary. For example, it can have a presentation layer, and a person who is architecting can think of having a separate layer called API layer, and then comes the business logic layer, because a presentation layer talks to the facade layer, which is API layer, and then it goes and talk to business logic layer, and there may be something called an integration layer, and then a separate thing called data access layer, where the data access layer may be just responsible to fetch data from different data sources, and integration layer may be doing some common orchestration when it comes to accessing data from different data sources and then doing the orchestration. So where the integration may be happening in both the integration layer and the data access layer. So this is the n-tier layered architecture, right? And then if you look at another architecture type called the microkernel architecture, where there may be a core component, and then it may be doing some integrations, but you may have other components brought in as plugins, and where those plugins may be doing different integrations, based on what the plugin is supposed to do. So this kind of an architecture is not very popular when it comes to developing enterprise applications. But if you are developing an enterprise application as a product, such as like when you're designing an ESB type of product, like a enterprise service bus type of product, you may have a core component, and then the other components could be brought in as plugins, like listeners, senders, and so forth, and or connectors when it comes to connecting with different heterogeneous systems and other data sources and so forth. However, some enterprise applications, may design their components as microkernel architecture, especially when they want to distribute a particular component, and that component update process itself is not in control of the distributor. In such cases, this architecture is useful, because you will not be modifying the core component, but you just bring in plugins, and you just do the deployment, and maybe do a few configurations. And so microkernel architecture may have uh, a place when it comes to enterprise integration as well, enterprise applications as well. And why do we need an enterprise integration architecture in the first place? So that is because EIA, or Enterprise Integration Architecture, serves as a fundamental tenet enabling seamless communication between different systems, right? And especially when you have different kinds of application that you need to create, you may want to like utilize a common functionality or common integration functionality shared across those different applications, right? And when that happens, your enterprise can be considered an integrated whole to have a unified integration method when it comes to how you develop different applications rather than individual applications having their own ways of integration. You need to have like a common way to do integrations, and that's what we target when it comes to enterprise integration architecture. So it enables interconnected business. Obviously, it enables and enhances operational efficiency, and end of the day, end user experience is uh, like enhanced when it comes to having a proper enterprise integration architecture, and it fuels the innovation, modernization, and finally the digital transformation of enterprises as well. And how do we go about building an enterprise integration architecture? It's something that you need to think very carefully, and when it comes to an enterprise, they need to first have a business architecture in place where you identify what are your business goals, and clearly identify who are the stakeholders and what systems are in place and what you need to accomplish when it comes to the business strategy. And that needs to be put in a diagram, which is what normally you call as a business architecture. And then when it comes to building an enterprise integration architecture, you need to see what are your existing technologies. It's very rare an enterprise gets the luxury to start on a greenfield type of a project, right? So they will always have something in place. But if you are having a greenfield uh, a project status, then you are in a lucky state, but hardly so, right? When it comes to uh, most of the enterprises, that's not the case. So they need to do an audit of existing technology to see what is already in place. And basically the step 3 and 4 can be it's not in a particular order, so you have to also choose the right technology when it comes to integration. And so those technologies should support different types of architectures that we are going to discuss in this demonstration, in this particular presentation. And then obviously you need to build the integration architecture, and that's not something that you will be done and dusted in a quick time. And this is an evolving process. It may take months and sometimes even years. And that's why you need to iterate and improve your architecture over and over again as your business evolve as well. So it's something that you keep evolving. It's something that you need to keep in mind. So let's look at the business architecture. This is a fictitious example of an e-commerce platform, right? So the e-commerce platform, what is your purpose? So you need to provide your customers with a unified view of all the products that you sell. And then you need to have a product taxonomy, all the product related details, recommendations, and then you need to create user profiles and then finally take orders. And this is not like uh, an exhaustive list of requirements when it comes to an e-commerce uh, platform, and it's a very simplified architecture, but in a real world it can be much more complex than this. And how you provide your customers that digital experience may be coming with a mobile application or a web application, and both of those needs to give a unified view so that consumers feel like you are accessing the same environment. That seamless user experience to consumers through multiple channel applications is a business focus. And then on the behind the scenes, how you fetch these data and what are the stakeholders and what are the other people involved also matters. And that's where the interconnected business and efficient operations come into play. And in case of an e-commerce platform, you may have a product catalog, systems of records. Suppliers may be involved when it comes to providing goods for you to sell through your e-commerce platform. And then payments, needs to be processed, and packaging and distribution is also an important aspect when it comes to e-commerce. So you have to have that business architecture laid out when it comes to building your enterprise integration architecture, because without understanding this, there is no point, and there will be no much value added in your integration architecture as well. So you need to have a clear understanding of business architecture. And then let's discuss a little bit about the main pillars of enterprise integration, right? Enterprise integration involves, at least in a theoretical sense, mainly three pillars. One is called the application integration, because enterprises will have multiple applications, and you need to connect these applications to break the silos and to get meaningful data out from multiple applications, and present it in your digital channels. And then also comes the process integration. It's not just the application, right? So when it comes to an order processing, and it's a business process, and how you go about really doing this business process, and how your orders from your customers uh, being taken in, and what systems needs to get affected internally, and how the distribution happens, how the packaging happens. All of these are like what we call the process integration. And when it comes to different systems, when you do the integration, that is what you call as the process integration. And then also there is this other pillar called data integration, because we spoke about systems of records, and you need to make sure you fetch data and do data processing from these different data sources, and that's what you call as data integration. So, what are the common integration scenarios in enterprises? And obviously, automations, like when it comes to process integration, automation plays a very important role. And in a technical sense, automations means you trigger an integration based on a timer, maybe. Like, we'll discuss some of these scenarios in the next section. And the other one is the AI integration. And in the modern context, AI is everywhere. So you need to make sure how you provide your applications with some intelligence, and so that your consumers feel the modernization that you have brought into your platform. And when it comes to integration as APIs, that has always been there. APIs have played a crucial role in integration for over a decade. And these integrations use API requests to trigger some processes, like some business processes, for example. And event-based integrations are also there. Now, it triggers based on some sort of an event. Now, you may have an integration like in terms of an e-commerce, for example, you just maybe based on a particular day or a season, you may want to do certain integrations, and those can be like event-based integrations. And obviously file-based integration, because when you are especially working with partners, and maybe even internal processes for reporting and so forth, you may want to create files, and these files needs to be transferred to different systems, and based on what is there in those files, different other integrations may also take place. So let's look at these individual pieces in order, and see how things work together. So when it comes to automations, now for example, as I mentioned, automation could be triggered based on a timer. Now, if you have a scenario where you want to fire a process every 1 hour, or start a process every 1 hour, and it could be like that process may involve connecting to CRM, and getting that data and transforming it, and doing further processing, and then inserting into a database. Maybe another automation could be doing your process every day at 11 p.m. So this is just once a day kind of an automation. The previous one was once an hour kind of an automation. So this once a day process, for example, could be fetching some data from databases. And let's say this is a batch process. And in such cases, you may have large number of information taken in at this stage, and you may want to do some sort of a parallel processing, and in which case you need to do some chunking and hand it over to a channel where things may be done in parallel. And whenever that process continues, and you may want to store this data in a cloud environment. And this may be an automation, right? So these are the kind of integrations that you see in enterprises today. And when it comes to AI integration, there are different patterns. And one of the easiest one is you have large language models like uh, OpenAI, like model providers, right? So OpenAI, Claude, basically Anthropic, and then DeepSeek, Gemini, and so forth, right? So these are like model providers, and they have large language models. And your users have a client application. That's how they see the experience. And you need to, because large language models can get a prompt or a sort of an input, like a fuzzy input, and respond back, right? So this prompt could be going as a textual format, and various other formats may be there, may need to be involved in, but let's think that it's text for the time being. Your integration could be taking in input from your users and sitting in the middle. And then you may have like model connectors in your integration, because depending on how you want to do the integration and to which model provider you want to do the integration, you may need to have some model connectors in place. So this is a typical integration that you can think of, a very simplistic one when it comes to doing AI integration. Another pattern that you see is something called retrieval augmented generation. Now, in the earlier case, you were just passing the prompt without any context. But what if you want to pass some context related to your own business data? So that's where you have your applications, and obviously now what we need to do is we have to pass in a prompt with some context. But this context comes from where? Now, we earlier looked at model connectors to connect with, and your application needs to connect with the model connector. And your context comes in the form of knowledge databases or knowledge bases, basically, which may be your own databases or your file systems, or in modern context you may hear these words called vector databases and graph databases and so forth. So your data may be residing in these places, so you need to have a way to fetch these data, and also to uh, ingest these data into these different data sources. And that's where your integration architecture should have a mechanism to connect with databases, vector databases, and so forth. And not just that, and that particular connector or the solution should have a mechanism to chunk your important enterprise level data and store it in these knowledge base, and then retrieve it later on, right? And this is what like once you get the data from these knowledge bases, your integration can do various tasks such as filtering those data and sanitizing those data, and then modify the prompt that was passed in by the users with some context. And that way the LLM can provide better answers when it comes to how it responds. Otherwise the answers are going to be very generic and so forth. So this is what the RAG pattern is like when it comes to AI integration. And the other thing that you see in today's context is AI agents. And these agents, again, you have model providers, you have applications, and let's look at someone who is playing the agent role. And in the agent role, obviously, just like in the previous case, you have model connectors, and this agent needs to be explained what its role is about, because you don't want a particular agent to be a superstar and know everything. And most probably these agents need to do one particular task well. And that's why you need to inform the agent about its role. And then obviously the agent needs to act on a certain uh, tools based on what the user is asking it to do. For example, this agent can be a scheduling agent, for example, scheduling an appointment with a doctor, for example, right? And when the user says that, and maybe the user converse with the agent, and it needs to act. And these tools can be coming in the form of functions or APIs, for example. Or in the modern world, you also hear this thing called model context protocol. Basically, one a way of exposing your APIs so that agents can easily connect, and it's basically a specification. So MCP specification is out there. So MCP servers maybe they are for agents to interact with. And apart from that, an agent may also have memory because users will not just be done and dusted with one single prompt and one single conversation. They will keep on conversing with it so that the agent needs to understand what the user previously asked. Basically, it provides the context retention, and gives personalization to your users. So all of these are mainly integration if you really look at it, and how you connect with the model provider from your agent, how your agent talks with these functions, APIs, and MCP servers. All of these are integration related, right? And this is something that you need to keep in mind when it comes to your integration architecture. And integration as APIs can be very useful. For example, one example could be you want to fetch some data from CRM when it comes to a REST API call that comes into your integration. And based on that, you may be connecting with a marketing system and then do some aggregation and then finally responding back to the caller who made the call with the REST API. So that may be one. And maybe you have a database and you want to expose those data or way to manipulate the data in the database as APIs. So this is what usually called a data service, and a good pattern when it comes to really following modern architectures, because your applications don't need to connect with your databases directly. Rather, it can go through this data service. So how that can be accomplished is through APIs. So integration as APIs. And another pattern can be something called a backend for front end. You may have a backend service, and your clients can be different types of clients, like a desktop client or a web client and a mobile client. Based on that, your clients needs its own customized API format, right? So such a case, for example, a web client may need a backend for front end for the web client, which is an API, and a backend for front end for mobile client. So why you need such a thing is because it may not be practical to have one single facade layer for all types of clients, right? So this is why this pattern is important, and your backend for front end may be connecting with another backend service, like one or many backend services. But this kind of a pattern may not be needed when it comes to GraphQL like APIs, because your clients can just request what it wants. But it's just a pattern, right? So somebody may choose to implement a BFF pattern when it comes to integration as APIs instead of GraphQL. But if you like GraphQL, you can go ahead with that as well. And the other thing is you may have multiple services, and those multiple services may need to be consolidated as a composite service before you expose that as another API, for example, for the clients to interact with. And this typically happens when it comes to modern APIs, because it then orchestrates between multiple other services as well. And then event-based integration, for example, you may have a requirement to listen and capture changes from databases, which we normally call change data capture. And that captured data you may want to put into two different channels, one into an event channel, another one into something like Kafka, for example, an event broker. And based on those, you can do parallel processing. And event brokers are good at publishing data to multiple subscribers, but rather even channels are just good at sending it to one single subscriber, and then those event handlers can make necessary uh, do necessary processing and make the integrations as necessary there. So this is basically one form of event-based integration. Another could be like you may have two data sources, right? And you want to read continuous stream of data from two sources, and those data you may want to correlate and see and filter those matching entries from those two different data sources, and then you want to maintain a window of 50 records every time. And then if you find a record, a matching record, let's say maybe you want to persist the correlated messages and 50 records prior to that. It's a business requirement, and this is an event-based integration. Uh, and because these two different sources may pump in data in different times, right? So that's why you need to have some level of persistence involved as well, right? And then finally, when you have such a correlation happens, maybe you might want to do some calculation of the average of those 50 records, some particular fields, and then you want to send that particular average in real time to a dashboard. So all of this can be a pattern that you find out in an event-based integration. And file-based integration, again, you may have remote SFTP locations, listen in for files and read file content, and then you do some level of transformation of the lines into a suitable format. And then you have a data service, and you may want to call this data service and do insertion one by one or as a batch. So this is a typical file-based integration that you may encounter in enterprises. Or you may, is a special case of streaming or basically event integration. But here in this case, it's coming from two different files, and you want to read stream of lines from both files and then filter out non-correlated records and correlate and enrich the records with the additional information that you may want to fetch from databases, and then you output a single file. So this is a file-based integration that you may come across. Now, I'm not saying this is the only type of integration that you see. You may see variations of this in your enterprises, and you need to have a mechanism to do these kind of integrations in your integration architecture. So we just discussed about various integration scenarios, but now let's talk about integration architectures, which is the main topic of this particular presentation, and topologies, right? So, like when it comes to how people used to do integration, the earlier days, people used to do point-to-point integration, and that also used to known as P2P integration or native integration. Why do we call that way? Now, let's imagine you have a service management uh, software and then a source code repository. And let's say in service management, one of your engineers or one of your service engineers mark a particular ticket that was created by uh, your customer as a product bug. And there is a requirement that such a bug is notified and sent to the product engineering team. Maybe you want to create a ticket automatically when this happens, and create an issue in this case. And here, the particular integration is done in the service management software itself. But the problem here is you are doing the integration in itself, in that software itself. But when you want to do more and more, when you have more and more software brought into the picture into your uh, in your enterprise, you'll be doing these kind of integration in those different places, which is not ideal. And this is why it is called point-to-point integration. And soon that is going to become a messier problem for you. So, but there are advantages as well. First thing is it's very simple to do, fast to implement, deploy, and run, less dependent on third-party systems because you're just doing that integration with whatever you have, right? And but when it comes to disadvantages, you are tightly coupling your integration with those systems. Difficult to scale, obviously, because now when you want to do more and more processing like that, you have to now think of scaling your service management software, right? Which may be expensive sometimes, right? And it also may be difficult to maintain in long term because now when you especially have like many systems in place, who is going to be responsible to learn all of these different systems? And maybe different teams might be managing these different systems. So maintaining in the long run is going to be very cumbersome for you. And also poor visibility and governance when it comes to, because your integration is now scattered in different systems, which is going to be a problematic situation for you. Right, and security risk for your systems is also in it may be a problem for you as well. And there is another type of an architecture called hub and spoke architecture, which kind of solves the problem that you had in point-to-point integration. Now, let's say you had two systems in place. So rather than doing your integration in those systems, you create your integration in a central place called hub. Now, when you have more systems brought in, doesn't matter, you still do your integration in the hub itself and so forth. So likewise, because when you have more and more systems added, you still manage everything centrally. But this architecture is much better than the point-to-point integration, but it also has problems. But let's first understand its advantages. It avoids implementing logic in all systems, obviously. Decouple systems of records, because now systems don't look at each other, or they don't talk to each other directly, but it goes through the hub. So it definitely decouples the systems of records. Integration managed by the central hub. But difficult to scale it as well. Now you have to now think of scaling the hub, which is fine, but now it can get bloated very soon, right? Because you have a lot of things in the hub. So how do you scale that without affecting everyone? You are just scaling it for one integration. Maybe CRM to ERP integration has more traffic now, but not the other integrations. Now you are just scaling that just because of two systems that needs to be scaled. So difficult to scale. Single point of failure. If something goes wrong, everything is down, and that's not a good thing. And which also means it's not cloud native. And this is where architectures like service-oriented architecture came in and helped in. So now, what is service-oriented architecture? It breaks down the application and integration logic to multiple reusable and composable services. And so, for example, you may in a service-oriented architecture, you may have multiple services like domain services, utility services, foundational services, and then your business service may be a combination of all of these. That's why it's composable, and you have broke down your application into different services, your integrations as different services. Like it could be utility services as maybe an integration service, or foundation service maybe an integration service, and these are now used by your business service. And in typical scenarios, you see in service-oriented architecture, mostly it was referring to SOAP, is a web services sort of a protocol. And it usually had something called a service contract, in which you had its interfaces and service operations listed down, along with maybe some service policies and service level agreements. And the actual implementation is different from that interface. And that's how it has been working, but it works really well. And traditionally, the service-oriented architecture has been tied with something called the service bus or enterprise service bus. So you have the service, you have the enterprise service bus that does some integration services and data services. And apart from that, you have these enterprise business processes running separately, maybe utilizing some aspects from the service bus as well. So all of these together, the boundary that you see on the right side is what makes the service-oriented architecture possible and traditionally. And obviously on the left side, you see the enterprise architecture, like clearly separated out with business architecture, information architecture, technology architecture, and application architecture. So it's sort of modern, and it was groundbreaking when this particular architecture style came into the picture, and which is relevant for integration as well. But it was more commoditized with tightly coupling that with the service bus, and that became a bottleneck. And a lot of people were thinking of this as a vendor locking mechanism, because a lot of different organizations started creating their own enterprise service buses, uh, and things became little messier. And especially with the SOAP specifications and baggages that it brought when it comes to web services specifications, like you usually call it the WS hyphen star or asterisk specification, like WS policy and WS reliable messaging and so forth. right? So that is what caused a little problem when it comes to service-oriented architecture. And there's another way of looking at it, like enterprise business process, this business process orchestration, and individual steps you may involve business services, right? And these business services sometimes may utilize integration services and so forth. So service-oriented architecture was great and it was working well and it solved a lot of problems that people had with point-to-point integration and hub and spoke integration as well. And it's a specialization of hub and spoke because now you separate out your business logic into business services, into integration logic into maybe separate integration services, and you have enterprise service bus doing the orchestration for you, and which was a groundbreaking technology at the time. And that's, for example, it works along with ESBs, Enterprise Service Bus. You had separate business services. Services are composable. ESB orchestrates the business services and provides wide variety of support for different protocol support for integrations like SOAP, data services, REST APIs, file integrations, JMS, WebSocket, and many more, right? And so it provided a lot of connectors to different systems as well, and that's where the integration took place. And microservices architecture became popular, and it could be thought of as an evolution of service-oriented architecture without the baggage and commoditized nature of the service-oriented architecture. So it doesn't depend on enterprise service bus. It doesn't have this like bulky specifications and so forth. So it just left the developers with a way to architect their applications and doing integrations without bringing in constraints, and that's what made MSA or microservices architecture very popular and much suitable for cloud nativeness and container nativeness, right? So it's an evolution of SOA. A service is a small, individual, independently deployable unit that does one unit of work. And for example, you have a microservice. An application is a collection of such small, loosely coupled services, right? You may have a collection of these services, and some of these services may be doing integration focus. Some of these services, for example, may be talking to your systems of records, and some business services can also do integration as well. So that's why there's no restriction as to what a particular service can and cannot do, but it's based on your understanding of what is suitable for your application and so forth. So and you don't be misguided with the term micro as well. So micro doesn't really mean your services needs to be tiny, teeny kind of a service, right? It just needs to handle one task, and that one task can be big sometimes, right? So it doesn't matter. So is microservices means your focus is like microscopic and not the size of the microservices, something that you need to keep in mind. And so this architecture was really good. And when it comes to how you go about designing your microservices is usually through APIs, but for that you can have different API architecture styles. Earlier days, people used to do SOAP. So again, in microservices architecture, your microservice could be a SOAP service. It doesn't matter that whether it is SOAP or REST, but what matters is there is no constraints when it comes to microservices architecture. It could be REST, for example, but when it comes to term API, people have always been referring that to REST APIs, unfortunately. But when it comes to APIs, it's not just REST, it's SOAP, it's REST, and in modern terms, could be GraphQL, gRPC, maybe even WebSocket, webhook types of APIs. So you had to choose a technology that can kind of cater to all these different types of architecture styles when it comes to creating your microservices. And so let's also look at the gateway architecture pattern. Now, you may have like microservices here, and you want to have an entry point from your consumer applications or your channel applications. It could be coming through something called a layer called an API gateway. Your API calls may be coming, and that may be orchestrating your calls into your microservices, one of the microservice, and which could trigger further orchestration, which may be doing integration with different systems. Or one of your microservice itself can act as a gateway. For example, in this case particular, this microservice is doing an integration, uh, and doing a business service. It's calling another business service, which is calling another service that is doing an integration. And here in this case, you may design another service as a thing that works along with other service, and but it does the work of an API gateway. Rather than doing a centralized API gateway, you just now did the gateway thing kind of consolidated as a service. So this is usually sometimes called a micro gateway, and because it's developed as a service or a microservice type of a gateway, and sometimes it's also called a sidecar because it just does a supportive role when it comes to the entire microservices architecture. And so these gateways could be doing API authorization, could do protocol translations, message transformations, rate limiting throttling, doing caching, and so forth. And that brings me to this topic called domain-driven design. And it's not related to integration in particular. It's an application architecture principle as well, but you can employ this design philosophy into your integration architecture as well. So what does it mean? So for example, in e-commerce side of the thing, there can be something called a shipping context. And within that shipping context, you may have multiple microservices, and so this is called a bounded context. And this bounded context may be interacting with or may have another context in the e-commerce world. It could be something called an order context. And within that order context boundary or that context, which is a business context, you have multiple services there. So microservices fit in really well into this domain-driven design philosophy. And maybe these two different contexts may be sharing data. Like this customer context may be involved in both the shipping context as well as the order context as well, right? And here the important thing is this bounded context is usually architected along with your business domain. And in the domain driven design, usually the technical people and the business people work together and they form a common language. In domain-driven design terminology, this is called a ubiquitous language, and which makes it easier to work with. So it promotes close collaboration with domain experts. Team can prioritize business critical integrations rather than just doing integration for the sake of doing or for technical reasons. It brings modularity into the picture. Flexibility and scalability is handled. But this particular design principle is very suitable for large enterprises with complex business domains and business specifications and so forth. May not be suitable for like a small organization. And event-driven architecture, we spoke about event integrations, but event-driven architecture, where you have an event where message brokers play a key part in this architecture, right? You may have something called an event queue, which does first in, first out type of a thing. You insert an event into an event queue, and then that event is processed in the order how it arrived by an event processor. So that's one style of doing event-driven architecture. The other one is something called the pub sub model, where event is published into rather than an event queue, you publish that into an event topic. And this event topic is capable of, publishing data to multiple subscribers. So these subscribers are the people who said, I am interested in whatever you get into the topic. And then event topic knows about it. Basically, the broker knows about these subscribers are interested in a particular topic, and when that topic gets a message, it just publishes that message into multiple event processes. Uh, and so forth, right? And it enables asynchronous communication, right? So why you say asynchronous communication? Because your publisher and the subscriber, in both the cases, need not be alive at the same time, right? So the publisher can just publish information without knowing who are the subscribers who are getting my messages and so forth. So that's why it enables asynchronous communication, suitable for high load use cases where the events will be kind of you do fire and forget, right? You just do the fire and you forget about what happens with that particular event. And it's suitable for high load use cases. And it's dynamic, particularly in the PubSub case, because you can add further event processors based on your requirements without modifying anything else. Another event processor just needs to subscribe to the event topic, and the broker will know there is an additional event processor now, and you can publish that message to this additional event processor. And it's highly available and scalable as well. And one thing is, it's difficult to handle sequencing, especially when you are when it comes to pub sub model. When you let's say these event processors may get the events in different uh, time frames, and it may do the event processing in different speeds. And let's say you want to have a like particular sequencing handled. How are you going to do that thing? It's not impossible to do, but it's difficult to do. And storage and backlog as well, like especially when your event processes are not active, your event topic may have many thousands or even millions of data without a consumption for a period of time. You may want to have that message stored in for multiple days to give a chance for the event processors to come up and process those messages and so forth. So storage and backlog can become a bottleneck in this particular architecture, and it's challenging to handle transactions as well. Let's say when you have an event published to multiple event processors, and imagine all these event processors needs to either succeed or fail altogether. How are you going to handle that? And that is the type of thing you call as transactions. And it's a bit difficult to handle these transactions in this architecture, even though there are different mechanisms which we are not going to talk about in this particular presentation. And one of the topologies that you see, the event-driven architecture, is something called mediator topology, where let's say in the e-commerce side, you cancel an order, that you get into a cancel queue, and then you see a scenario where the cancellation can be like proceeded. So you need to check whether that can be done. Maybe you provide that to a cancel proceed queue, from which the cancel proceed check processor may get a message and check on that. But the next step needs to wait until the cancel proceed check uh, gets a response back, and maybe it may put that into a database. So the second step, you need to wait for it, and then let's assume it just got the clearance to proceed, and it will go on to the next step called cancel order. And that cancel order maybe publishing that information into a topic which may be interested by three different subscribers, maybe inventory update processor, shipping update processor, and payment refund processor. And all of this either needs to work together in transaction. So imagine that all of this needs to work together, and how you exactly tackle that, we are not going to discuss, but it's a challenging situation which can be tackled in various forms in this architecture, right? And then finally you notify asynchronously by doing a notification queue, and then a notification processor may do the job for you. But here, this architecture, there is a wait. For example, the event mediator does the job of orchestrating the cancel order event that came in the first place, but the second step had to wait on the first step. So that's for that reason, for this particular scenario, event mediator topology pattern is not that good, because it just waits and polls on the information. This pattern is good when every step that you are taking care of in the event mediator does not depend on the previous step. But here in this case, the second step depends on the first step, so it has to wait. So if your scenario doesn't have such a requirement, event mediator topology is a good choice. So and there is another topology called broker topology, which is good when it comes to especially non-waiting scenarios, right? So for example, this is another pattern. So you have a cancel order queue, cancel proceed check goes on, and when that goes on, let's say you cancel proceed check is a particular process. It's not a queue or anything. Uh, so cancel proceed check processor uh, takes the cancellation queue, it checks, and if it's successful, it just publishes the event to cancel order topic and at the same time for the notification topic. And the cancel order topic can do the job just like in the previous case, and the notification process can do the job in parallel as well. So you can employ such a mechanism into place as well. This kind of an architecture is called broker topology. And when it comes to integration, you might also come across streaming architectures. So in this case, you may have data coming in live, real time from data streams from different streaming systems, SaaS applications, enterprise systems, real time events, and also data at rest may need to be fetched in batch form. Like you may want to extract data from cloud storage, flat files, databases, and data lakes. And then you put that data into a stream processing engine where you may want to do transformation, you may want to do filtering, basically cleansing, doing aggregation and correlation, just like we previously described. When it comes to event integration, it may be related to streaming integration. And then finally, you may want to publish your correlated events, your aggregated events, enriched events into another streaming consumer or to a data store, something like that. So this is another type of architecture that you may employ into your enterprise integration architecture. And finally, we also need to quickly talk about integration patterns. Now, this is not particularly an architectural thing, but when it comes to your individual integration implementation, you can employ the very well documented and learned patterns when it comes to how to do integration with different systems. Now, for example, some of these patterns are on a broad case. We describe that as integration architectures. For example, event-driven consumer is an architecture. You can just put it into event-driven architecture and so forth. So basically, this actually comes from a book called Enterprise Integration Patterns from Gregory Hope. And it has about 65 or so patterns documented. There is also a dedicated website on this, and I recommend you refer to these things. I hope I am planning to create another video on these integration patterns, some of the common ones. But let's look at one pattern, maybe something called pipes and filter. So you may have an incoming order that may go into, because it may be coming in an encrypted format, your the filter uh, here the pipe is basically an API call in the first diagram, the top diagram, and you may be doing the decryption, and then you do an authentication service over a pipe. That pipe is an HTTP call here in this case, let's say, and the filter in that step is to do some authentication after decrypting the message, extracting some information from your payload and doing the authentication. And then you do another call with the payload where, let's say, in this incoming order, you may have duplicated orders. Let's assume that way. So at that filter stage, maybe you do deduplication, eliminating duplicated orders, and then you send it to another channel or another entity with a clean order. So, so this kind of scenario, you can also think of a pipe with an event queue to bring in asynchronous nature into the picture as well. So we are instead of an API call, you do just fire and forget, and the remaining steps uh, is remains as is, right? And it does the same thing, except the HTTP call here in this case, it goes through uh, an event queue. Let's finally, wrap up this session with a deployment architecture. So let's talk about a centralized ESB style architecture. Let's say, obviously, when it comes to integration with various architectures, you finally have to implement your integration, either your microservices, your integration services, business services, and so forth. You implement that, and then you connect with the systems of records, then you test and you commit that code into a repository, like a code repository, and then you have your development environment, let's say, where you want to have your integration runtime, because now ESB style, right? So this, your integration is an ESB here, and it may be fronted by a gateway because of the gateway pattern that we described. You may have CI/CD process that fetch your integration logic from your GitHub repository, and then do the deployment into your development environment. Likewise, your let's say another environment, a pre-production environment, you may have one integration, but now you want to do a little bit of a clustering uh, for high availability, and that's why you connect your ESB integrations into with a database maybe, and to a file system, and you may have a gateway and do your test environment deployment into the file system, so that both the integration can have a view of it, rather than doing the deployment into individual integration runtimes. So that may be a pattern that you might want to look at. Your production, you start with a high availability setup, just like in the test environment, you have a gateway, do the deployment, but later you may want to do expansions, like you scale your deployment with multiple other integration runtimes as well, but it's all centralized, right? So you have a logic. So microservices architecture is little different, but still the process is somewhat the same. So you implement your microservice, test, commit it, and now like in the domain driven design, you have like a domain identified, and you had done that implementation, and you can deploy just like you did it previously with the centralized deployment, centralized ESB style deployment. Here, you rather do the contextual, that bounded deployment can come in the form of a bundle. All right, so these bundles can be, for example, containers as well, like Docker containers. But let's assume even without Docker containers, you can do the deployment in this way logically. But it's going to be difficult because of without those containers, without having some sort of an orchestration for containers, microservices deployment can become really messy. But you can do that. So that's what. So we are just explaining here. And now see in your one of the context, now you need to do a little bit of a scaling, where you need to have instead of one microservice, you have to have two, and so forth, right? And let's say this is the test environment, and your production environment, again within your bounded context, your individual microservices you may have to scale, and you need to have mechanisms to do that thing. And your job, your CI/CD job, needs to make sure that it does that work uh, properly. But this is where microservices architecture is better uh, done in a Kubernetes kind of a container orchestration requirement, because easily management of all of these microservices is going to become a nightmare very soon if you have like thousands of microservices come into play, and it can easily become a mesh or a mess. So in Kubernetes, you do the same thing, but you rather have, instead of different virtual machines or physical machines, you have a cluster, a Kubernetes cluster, where multiple worker nodes are there, and you have a development job, and your development job basically uses kubectl commands to fetch data or your microservices from your code repository, in which case you probably would have Dockerized it, and it does the deployment into development environment. Now, because it's packaged into containers, your deployment is going to be much easier, and scaling is also going to be much easier, right? So here in this case, you see this red color service bounded context. Now you have two uh, instances running. Basically, the Kubernetes world, it's pods, two pods running in two different worker nodes and so forth, right? And also you see your uh, other services are also running in that way. So, and in the production environment as well, you may have different services, different pods running in different worker nodes, which you don't need to worry about because Kubernetes concepts like services and ingress does this abstraction very well for you. So basically, all of this you need to consider when it comes to enterprise integration architecture. So we spoke about uh, application architectures and where integration fits in there. And we spoke about application architecture and integration architecture topologies like point-to-point, hub and spoke, service-oriented architecture, microservices architecture, event-driven architecture, and so forth. And we looked at event-driven uh, topologies like mediator topology as well as broker topology. We looked at domain-driven design, and then finally, we also looked at various different deployment architectures when it comes to centralized DSB, microservices deployment architecture, and that microservices architecture extended into Kubernetes like architecture as well. So this brings to the end of my session. It was a bit lengthy session, but I just wanted to cover all these architectural aspects as well. This is one of the talk that I gave in another conference, so I just removed some of the contextual information related to that conference and made it a common video to publish it in my own YouTube channel. So please subscribe to channel for more videos like this, and and also subscribe and enable the notification for you to get information related to new videos as well. So I see you in another new video very soon, and some of that could be on integration patterns, domain-driven design, and so forth, and some of the other modern architecture styles when it comes to application and integration. See you soon. Thank you very much.